Welcome back to lectures on radioactivity. This is part 8. Today we'll be considering more examples on calculations in radioactivity. This is to help us appreciate how to use the already stated formulas that we made available in previous lectures. So let's see the examples now. Number 1. A radioactive substance has a half-life of 6 hours. How much of 48 grams remains after 18 hours? Okay, we have two methods of solving this problem. The first method, this is the original mass of the substance, and as at this time nothing really is happening, so we'll assign it T naught. When it undergoes at the first half-life, rather, remember what we did before, the radioactive substance is halved. Remember we said half-life is the time taken for half the substance to decay. So if we take half of this now, that will give us 24. That's the first half-life. And we're told in the question that the half-life is 6 hours. So the first half-life is 6 hours. We'll bring this here and make it undergo another process of division. In other words, if we half it again to get 12, that will be 2 half-lives. And then 2 times 6, that is 12 hours. If we half it again to get 6, that's 3 hours, 3 half-lives rather. So 3 half-lives, that's 3 times 6, that's 18 hours. We're actually told to stop at 18 hours. So 18 hours, we have 6 grams. So 6 grams is what is left. Alternatively, we can use this formula. You're familiar with this formula. I asked you the other time to commit these formulas to memory. So M naught is M times 2 raised to the power T over T half. The original mass given in the question is 48. We're told to get the mass that is left after it has undergone disintegration. We're given that the time for the disintegration is 18 and the half-life is 6. So if you divide 18 by 6, you get 3. 2 raised to the power 3 is 8, and if you resolve this properly, you will get 8m equal to 48. So m is 48 over 8, and then you get 6 as your answer. Question number 2. A sample initially contains 1,600 atoms. How many atoms remain after 4 half-lives? And so remember this formula. I told you to commit this formula to memory. N naught over 2 raised to the power n is nt half, where n is the number of half-lives. The number of half-lives in this question now is 4. And so if we integrate that into the formula, we have n is the number of atoms remaining after disintegration. And so that would be the original number of atoms, 1,600 over 2 raised to the power 4. 2 raised to the power 4 is 16. If you do 16 divided by, 1,600 divided by 16, that will give us 100 atoms. So 100 atoms are left after the disintegration. Alternatively, we have 1,600 atoms. As at this time, nothing exactly is happening. When it is halved, as we get our first half-life, you half it. Second half-life, that's the second half-life, you have that again. So 1600 divided by 2, that will give us 800. The second half-life occurs by dividing that by 2 again. That will be 800 divided by 2. That will be 400. The third half-life, dividing 400 by 2, that will be 200. The fourth half-life, dividing 200 by 2, you end up with 100 atoms. We are told to find the number of atoms. In other words, how many atoms remain after 4 half-lives. We go to question number 3. A radioactive element decays from 120 gram to 15 gram in 20 days. Determine its half-life. You remember this formula again? I once asked you to commit this formula to memory. M0 is equal to M times 2 raised to the power T over T half. That's half-life. We're told that the radioactive substance decays from 120 to 15. So M0 is 120 and then M is 15. So the original mass is 120 and the mass left after disintegration is 15. Then we're given that the whole process of disintegration took 20 days. So 20 over T half. Dividing both sides by 15, you get 8. 8 is 2 raised to the power 3, so we equate the powers. On equating the powers, we're going to be left with 3 is equal to 20 over T half. So T half times 20 over 3. And eventually we have 6 number 2 over 3 days. So our half-life is 6 number 2 over 3 days. Question number 4. An isotope contains 20 protons and 24 neutrons. Find, that's A now, its mass number. B, determine whether it is likely to be stable or unstable. Remember, mass number, nuclear number, is number of protons plus number of neutrons. So if you add the number of protons, 20, number of neutrons, 24, that will give you 44. So our mass number is 44. To determine whether it is stable or not, we will use the neutron-proton ratio. The neutron-proton ratio, that's number of neutrons over number of protons. Number of neutrons, 24. Number of protons, 20. By the time you resolve that, you're going to get 1.2. Remember we said that for non-radioactive element, that means for stable nucleus, the neutron-proton ratio lies between 1 and 1.5. But here we got 1.2, so it means that the isotope is stable. Question number 5. The atomic number of an element is 26 and its neutron-proton ratio is 1.5. Calculate the number of neutrons and its mass number. Again, don't forget the neutron-proton ratio is number of neutrons over number of protons. We are given the neutron-proton ratio to be 1.15. We are told to look for number of neutrons. We are given the atomic number to be 26. Don't forget, atomic number is the number of protons in the nucleus of an atom. So the number of protons then is 26. If you cross multiply, number of neutrons then becomes 26 times 1.15. That will give us 29.9, approximately 30. So mass number then is number of protons plus number of neutrons. Number of protons, 26. Number of neutrons, 30. Our mass number then becomes 56.